You know what's strange about studying ancient texts? Most of the time, you're dealing with metaphor, poetry, symbolic language that was never meant to be taken literally. A prophet writes about stars falling from heaven, and scholars understand it as apocalyptic imagery, not astronomical observation. Someone describes a fiery chariot in the sky, and we file it under mythology, religious vision, cultural narrative. The assumption, usually correct, is that ancient people were describing their subjective experiences, their fears and hopes and spiritual frameworks, not making precise records of celestial phenomena. But sometimes, just sometimes, the metaphor turns out to be memory. And when that happens, when ancient text and modern data align in ways that shouldn't be possible, everything we thought we understood about both history and astronomy gets called into question. This is one of those times, and it started, like so many archaeological discoveries, with a fragment of parchment that nobody was paying much attention to. The Dead Sea Scrolls are probably familiar to you, at least in general terms. Ancient manuscripts discovered in caves near Qumran between 1947 and 1956, hidden there by a Jewish sect around the time of the Roman occupation, preserved for 2,000 years in the dry desert climate. They include biblical texts, commentaries, community rules, apocalyptic writings. Scholars have been studying them for decades, translating fragments, piecing together documents, arguing over interpretations. It's one of the most important manuscript finds in history, a window into Judaism and early Christianity at a crucial moment in their development. Among the scrolls is a document cataloged as 4Q171, what scholars call a pesher. That's a type of commentary where ancient scribes would take passages from older texts, usually prophetic books, and interpret them as referring to events in their own time. The word pesher means interpretation or solution, like you're solving a puzzle, finding the hidden meaning in scripture. 4Q171 specifically is a pesher on Psalms, taking verses from the biblical Psalms and explaining what they really mean in light of current events, at least current from the perspective of someone writing 2,000 years ago. The scroll has been known for decades. Parts of it were published, translated, analyzed in academic journals. Nothing particularly surprising in the standard sections. Typical pesher material, connecting ancient psalms to the sect's beliefs about the end times, their conflicts with the Jerusalem priesthood, their expectations of coming judgment, important for understanding the community, but not the kind of thing that makes headlines or rewrites history books. But here's what you need to know about ancient manuscripts. They don't come out of the ground complete. They come out as fragments, pieces, scraps of parchment that have deteriorated over millennia. Scrolls get damaged by moisture, eaten by insects, torn apart when caves collapse or get looted. What we have of 4Q171 is incomplete, with gaps where text is missing, sections where the parchment has disintegrated. For years, scholars worked with what was available, reconstructed as much as they could, and accepted that some parts were lost forever. Except they weren't lost. Not all of them. The Israel Antiquities Authority has been conducting ongoing conservation and analysis of scroll fragments for decades, using increasingly sophisticated imaging techniques to read text from damaged parchment that was previously illegible. Multispectral imaging, infrared photography, advanced computer processing to enhance faint ink traces. And in storage, in the climate-controlled facilities where the scrolls are kept, there are thousands of tiny fragments that were collected from the Qumran caves but never successfully matched to known documents. Pieces too small or too damaged to identify, waiting for technology to catch up. In late 2024, a team from Hebrew University was doing routine imaging work on unidentified fragments, part of a long-term project to catalog everything in the IAA collection. Dr. Sarah Mizrahi, a specialist in Second Temple period texts, was processing a batch of fragments labeled as 4Q-Miss, meaning they might be from Cave 4 at Qumran, but hadn't been definitively assigned to any specific scroll. Most of them were blank or had only a few illegible letters, but one piece, about 4 centimeters by 6 centimeters, showed clear Hebrew text under infrared imaging. Old Hebrew, the script style consistent with 1st century BCE or 1st century CE, and when Mizrahi started translating it, she realized it didn't sound like typical biblical commentary. The text read, in her initial translation, "In the days of great tribulation, the wandering star shall return from the depths of the void, clothed in ice and fire, bearing witness to the appointed time. Its tail shall stretch across the heavens like a banner of judgment, visible to all nations. By its path shall the wise know the seasons." Standard apocalyptic language, sure. Stars and fire and judgment, except for one thing. The phrase wandering star in Hebrew is kafkg hnvdd, kokav hay noted, a term that doesn't appear in biblical Hebrew. It's unusual, and the description that follows, clothed in ice and fire, with a tail stretched across the heavens, sounds less like metaphorical imagery and more like someone describing a comet. Ancient people did observe comets, of course. Chinese astronomers kept detailed records. Greek and Roman writers mentioned them. They were usually interpreted as omens, signs of disaster or divine intervention, but the observations themselves were real. What caught Mizrahi's attention was the specificity. Not just a comet will appear, but the wandering star shall return. Return implies periodicity, implies this is something that comes back, something predictable. And the phrase, "By its path shall the wise know the seasons," suggests not just observation, but calculation, astronomical knowledge. She flagged the fragment for further analysis, brought in colleagues from the Hebrew University Astronomy Department, showed them the text. They were intrigued, but cautious. Ancient people had sophisticated astronomical knowledge in some areas, particularly regarding the sun, moon, and planets, but periodic comets with return intervals longer than human lifetimes, that's harder to verify through ancient observation. Halley's Comet was the first to have its periodicity confirmed by Edmund Halley in 1705, and that only worked because the historical records were good enough to trace it back through multiple returns. For an ancient scribe to know that a particular comet would return required either lucky coincidence or observational records spanning centuries. But then came the carbon dating, and everything got more interesting. The Israel Antiquities Authority has strict protocols for dating manuscript fragments. They use accelerator mass spectrometry, AMS radiocarbon dating, which can date very small samples of organic material with high precision. For 4 Q171 fragments, previous dating had placed the scroll composition somewhere between 50 BCE and 50 CE, a 100-year window consistent with other Qumran materials. This new fragment underwent the same process, and the results came back with a narrower range, 20 BCE to 30 CE, plus or minus 20 years. That places it right around the turn of the era, the time period when the Qumran community was most active, when the Roman Empire controlled Judea, when whoever wrote this text was living and observing the sky. Now, you probably see where this is going. 3I Atlas passed through our solar system in 2025. It came from interstellar space, made its closest approach to the sun in late October, swung past Earth in December, and is now outbound, heading back into the dark between stars. We know its trajectory. We know its velocity. We've calculated its orbit with high precision. And when astronomers started doing the calculations, tracing 3I Atlas path backward through time, they found something remarkable. Based on its current trajectory and velocity, accounting for gravitational perturbations from the sun and planets, 3I Atlas was last in the inner solar system approximately 2,000 years ago. The uncertainty in the calculation is substantial, orbital mechanics that far back gets complicated, but the central estimate puts its previous perihelion passage somewhere around 25 CE, plus or minus 50 years. The overlap with the radiocarbon date of the fragment is too close to ignore. The scroll fragment was written between 20 BCE and 30 CE. The comet was likely visible from Earth around the same time, give or take a few decades. Could be coincidence. Could be the writer was describing a different comet, or using conventional apocalyptic language that happened to sound like a comet description. But then Dr. Avi Goldstein from Tel Aviv University, who specializes in ancient astronomical texts, started looking more carefully at the Hebrew wording, and he found something that made coincidence much less likely. The text, in the lines following the initial description, includes what appears to be a date and a position reference. Ancient Hebrew texts sometimes include astronomical information coded in unconventional ways, using number values assigned to letters, using poetic descriptions that map to sky coordinates if you know how to read them. Goldstein spent 2 weeks analyzing the fragment, consulting with other specialists in ancient astronomy and Hebrew numerology, and he concluded that the text contains a specific sky position, a reference to the constellation that Greek astronomers called Lyra, the lyre, and that appears in Jewish tradition as Kinnur, David's harp. Lyra, the same region of sky that 3I Atlas came from when it entered our solar system in 2025. The same constellation where the Euclid telescope found 47 objects with identical spectral signatures, 6 of them on trajectories toward us. Now here's an ancient text, written 2,000 years ago, describing a wandering star that returns from a specific region of the heavens, and that region matches the origin point of the interstellar object we just watched pass through our solar system. Let's talk about what the fragment actually says, because the details matter here. Ancient apocalyptic texts are full of cosmic imagery, and if you cherry-pick phrases, you can make them say almost anything. The sun will go dark, the moon will turn to blood, stars will fall from heaven. Standard end times rhetoric that appears across multiple cultures and time periods. So when we're claiming that an ancient text describes a specific astronomical event, we need to be rigorous about what the text contains versus what we're reading into it. Dr. Goldstein's team spent months doing exactly that kind of rigorous analysis, and what they found goes beyond vague symbolism. The fragment, as reconstructed from infrared imaging and careful translation, contains approximately 12 lines of Hebrew text. Some words are damaged or missing, requiring educated guessing based on context and comparison with similar texts, but the core content is clear enough. After the opening description of the wandering star returning from the void, the text continues with what appears to be observational details. It describes the star's appearance changing over time, growing brighter as it approached, developing a visible tail that stretched across multiple constellations. It mentions the star being visible in the eastern sky before dawn during certain months, then shifting to evening visibility as it moved through its cycle. That's not generic apocalyptic imagery. That's a description of a comet's behavior as seen from Earth. Comets do exactly what the text describes. They start as faint points of light, often visible only with good eyes and dark skies. As they approach the sun and heat up, they get brighter, develop tails of gas and dust that can stretch millions of kilometers. Their position relative to the sun changes throughout their orbit, making them morning objects for part of the apparition and evening objects for another part. Someone watching a bright comet over the course of weeks or months would see exactly the progression the text describes. But here's what makes it more than just a comet observation. The fragment includes what Goldstein identifies as duration markers. Ancient Hebrew texts sometimes use specific phrases to indicate time spans, and this fragment has several. It mentions the star being visible for a season and part of a season, which in Second Temple period usage typically means somewhere between 4 and 6 months. It describes the star reaching maximum brightness in the month of gathering, which correlates to late autumn in the Jewish calendar, and it states that the star's tail reached its greatest extent when winter solstice had passed, placing peak activity in late December or early January. Now compare that to what we know about 3I Atlas passage through the inner solar system in 2025. The comet was first detected in July, became visible to amateur observers by September, reached peak brightness in late October through November, made its closest Earth approach in mid-December, and remained visible until January before fading as it moved outward. The timeline described in the ancient text matches the modern observation timeline within the constraints of ancient timekeeping precision. Someone watching 3I Atlas 2,000 years ago would have seen almost exactly what the fragment describes. The position information is even more specific. Ancient astronomers didn't use the modern coordinate system of right ascension and declination, but they did track celestial objects relative to recognizable star patterns. The fragment mentions the wandering star passing through the strings of the harp, which Goldstein interprets as movement through the constellation Lyra. It describes the star coming from the region of the Eagle, which maps to Aquila, a constellation adjacent to Lyra, and it notes the star's path taking it toward the Twins, which would be Gemini, a constellation that sits along the ecliptic plane where comets often appear when viewed from Earth. Those positional references match 3I Atlas' apparent path across the sky as it would have been visible 2,000 years ago. The comet's entry trajectory brought it from the direction of Lyra, passing through regions of sky near Aquila and other northern constellations, eventually becoming visible in the pre-dawn sky in late autumn, in positions that would place it moving toward the zodiacal constellations, including Gemini. The ancient observer got the path right, got the general timeline right, got the behavior right, either through extremely lucky coincidence or through actual observation of the same object on its previous pass. Dr. Mizrahi and her team wanted to be absolutely certain they weren't manufacturing correlations from ambiguous text, so they brought in independent translators who didn't know the context. They gave them the Hebrew text without mentioning anything about comets or 3I Atlas, just asked for accurate translation and interpretation. All three independent translators came back with versions that described a moving celestial object with a tail, visible for several months, following a specific path through the northern sky. The consistency across translations ruled out the possibility that they were forcing the text to say something it didn't actually mean. But translation is only part of the verification process. They also needed to confirm the carbon dating results, make sure the fragment really was as old as the initial test suggested. The IAA sent samples to 3 different radiocarbon laboratories, using different preparation methods and different AMS systems. The Oxford Radiocarbon Accelerator Unit, the ETH Zurich Laboratory, and the University of Arizona AMS facility all tested samples from the same fragment. The results came back within tight agreement. 1995 years plus or minus 35 years before present, with present defined as 1950 CE in radiocarbon convention. That puts the parchment creation between 45 BCE and 15 CE, with highest probability around 15 BCE to 5 CE. The uncertainty overlap with the calculated 3i Atlas perihelion is substantial. We can't say for certain that the text was written during the exact passage of the comet. Ancient manuscripts sometimes describe past events, sometimes contain prophecies about future events, but the convergence of evidence, the physical age of the document, the astronomical details in the text, the positional references, the timeline descriptions, creates a compelling case that whoever wrote this fragment was either observing or had access to observations of a bright comet that appeared around the turn of the Common Era and followed a path consistent with 3i Atlas calculated trajectory. Now, ancient astronomical records from that time period are fragmentary and scattered across different cultures. We don't have a comprehensive catalog of every comet seen in ancient times. Some were recorded, particularly bright ones that Chinese astronomers noted in their official dynastic histories. Some appear in Roman texts as omens associated with major events like the death of Julius Caesar or the birth of emperors. But the historical record has gaps, especially for observations made in regions like Judea that weren't systematically cataloging celestial phenomena. Dr. Michael Zhang from Beijing, Normal University, a specialist in ancient Chinese astronomical records, got involved when news of the fragment started circulating through academic networks. He went back through the Han Dynasty chronicles, looking for any mention of unusual celestial objects around the relevant time period, and he found something interesting. The Han Shu, the official history of the Western Han Dynasty compiled in the 1st century CE, contains a brief entry for the year 5 BCE, recording a broom star appearing in the eastern sky during autumn, visible for approximately 4 months. Broom star is the traditional Chinese term for comets, referring to their swept-back tails. The Chinese record doesn't include the kind of detailed position information the Dead Sea Fragment has, just notes that it appeared in the east and was visible for an extended period. But the timing aligns. 5 BCE falls within the radiocarbon date range for the fragment, falls within the uncertainty range for 3i Atlas calculated previous perihelion, and matches the description of autumn visibility. Zhang found 2 other possible references in fragmentary texts from neighboring regions, one from Korean chronicles and one from Japanese records, both mentioning unusual celestial phenomena around the same time period, though the details are too sparse to confirm they're describing the same object. What's striking is that we have independent records from multiple cultures separated by thousands of kilometers, all potentially describing the same event. The Dead Sea Fragment from Judea, the Han Chronicle from China, possibly Korean and Japanese observations. If 3i Atlas was as bright during its previous pass as it was in 2025, it would have been visible across most of the northern hemisphere for months. Different observers would have recorded it according to their own cultural frameworks and astronomical traditions, but they would all have been watching the same object. The European astronomical records from that period are less helpful. Roman texts mention comets occasionally, usually in the context of omens and portents rather than systematic observation. There's a famous comet recorded in connection with Augustus Caesar around 12 BCE, but the descriptions don't match the Dead Sea Fragment's details. Greek astronomical texts from the era are more scientific in approach, but most have been lost, and what survives tends to focus on planets and eclipses rather than transient phenomena like comets. So we're left with fragmentary evidence from multiple sources, all pointing toward a bright comet visible around the turn of the era, with the most detailed description coming from an ancient Hebrew text that matches the calculated behavior and position of 3i Atlas. That's enough to make the connection plausible, but it's not proof in the definitive sense. Ancient astronomy is full of uncertain identifications and tentative correlations. Without time machines, we can't go back and verify directly. But here's where the finding becomes more than just an interesting historical correlation. Here's where it starts to fundamentally change what we thought we knew about 3i Atlas. Because if the ancient text is describing the same object we observed in 2025, if 3i Atlas really was visible from Earth 2,000 years ago, then it's not an interstellar visitor in the way we've been understanding that term. It's something else entirely. Something that challenges our basic assumptions about where these objects come from and what they're doing. When 3i Atlas was first confirmed as interstellar, the calculations were straightforward. You measure its velocity, measure its trajectory, account for the sun's gravitational influence, and work backward to figure out where it came from. The numbers showed an object moving faster than solar escape velocity, coming from outside the solar system, following a hyperbolic trajectory that would take it back out into interstellar space after its brief swing through our neighborhood. Classic interstellar visitor, same basic profile as Oumuamua and Borisov. An object from another star system, ejected by gravitational interactions, wandering through the galaxy for millions of years until it happened to pass close enough to our sun to be detected. But that interpretation assumed this was a one-time event. a random encounter between our solar system and a piece of debris from elsewhere in the galaxy. The probability calculations suggested we should see maybe 1 or 2 such objects per year if we had perfect detection capabilities, with most of them passing through the outer solar system unnoticed. Finding 3 in less than a decade seemed consistent with those predictions, especially as our survey capabilities improved. A periodic return changes everything. If 3i Atlas was here 2,000 years ago and came back in 2025, it's not on an escape trajectory. It can't be. Objects on escape trajectories don't come back. They leave and keep going, accelerated beyond the sun's ability to recapture them. For 3i Atlas to return, its orbit must be bound to something. Either it's in a very long elliptical orbit around the sun, with a period of approximately 2,000 years, or it's in orbit around something else that brings it back through our region of space on a regular cycle. Dr. Catherine Volk at the Lunar and Planetary Laboratory in Arizona was one of the first astronomers to work through the orbital implications. She took the observed trajectory of 3i Atlas from 2025, the estimated previous perihelion date around 5 BCE, based on the historical records, and tried to calculate what kind of orbit would connect those 2 points. The math is complicated because you're working backward through 2,000 years of gravitational interactions with planets, accounting for perturbations that accumulate over multiple orbits, dealing with uncertainties in the initial conditions. But even with the uncertainties, certain patterns emerge. If 3i Atlas is in a bound orbit around the sun with a 2,000-year period, its aphelion, the farthest point from the sun, would be somewhere around 250 to 300 astronomical units. That's way out past the Kuiper belt, past the scattered disk, deep into what we think of as the inner Oort cloud region. Objects in those orbits move incredibly slowly at aphelion, creeping through space at velocities measured in meters per second rather than kilometers. They spend most of their orbital period in the cold outer reaches, and only briefly swing through the inner system where we can see them. The problem with that scenario is that 3i Atlas observed velocity was too high. When you calculate the expected velocity for an object at perihelion in a 2,000-year orbit, you get numbers significantly lower than what we measured. The object was moving too fast to be in a simple elliptical orbit around the sun with that period. You can try to account for the discrepancy with planetary perturbations, gravitational assist from Jupiter or Saturn during previous passes, but the numbers don't quite work. The velocity excess suggests energy input from somewhere else, some factor not accounted for in standard orbital mechanics. That brings us back to the alternative: what if 3i Atlas isn't primarily orbiting the sun? What if it's orbiting something else? Something massive enough to keep it bound, and that something is itself, moving through our region of space on a cycle that brings 3i Atlas past Earth every couple thousand years? A rogue planet would fit. A massive object, maybe several Earth masses or more, in a wide orbit around the sun, or possibly even unbound, but moving slowly enough relative to the sun that it stays in the general neighborhood for long timescales. Remember the 47 objects Euclid found, all with identical spectral signatures to 3i Atlas, scattered across nearby interstellar space with 6 of them on inbound trajectories? What if those aren't individual random objects? What if they're part of a system, a swarm of smaller bodies all orbiting a central mass that we haven't detected yet because it's dark and cold and difficult to see? A wandering planetary system passing through our region of the galaxy, close enough that its outer population of comets and asteroids occasionally gets perturbed into crossing paths with Earth. That hypothesis explains several things that the simple interstellar visitor model doesn't. It explains why 3i Atlas returned. It explains why the Euclid objects all have identical chemistry, they're from the same parent system. It explains the directional bias, why several of them are heading toward us. They're all responding to the gravitational influence of their shared primary mass as it moves through local space. And it explains the ancient records, because if the system has been in our neighborhood for thousands of years or longer, ancient observers would have seen multiple objects from it, particularly during close approaches. But it also raises deeply troubling questions. If there's a massive rogue planet or brown dwarf moving through the inner solar system's general vicinity, why haven't we detected it directly? We have infrared surveys that should spot anything that warm, gravitational surveys that should catch the lensing signature of anything that massive. The WISE mission mapped the entire sky in infrared, looking for exactly this kind of object. Subsequent analysis has ruled out anything Saturn mass or larger within a certain distance. So either the hypothetical primary mass is smaller than that, or it's farther away than we think, or there's something wrong with our detection methods. Dr. Volk's team ran population simulations, trying to figure out what kind of central body could explain the observations while evading detection. They found that a Neptune to super-Earth mass object, something in the range of 5 to 15 Earth masses, could work if it's currently positioned at the right distance and hasn't passed close enough to inner system bodies to cause obvious perturbations. That mass range is small enough to have escaped wise detection if it's distant enough and cold enough, but large enough to hold a population of cometary objects in bound orbits. Interestingly, that's similar to the mass estimates for Planet 9, the hypothetical planet that some astronomers think might exist in the outer solar system to explain the clustering of certain trans-Neptunian objects. But Planet 9, if it exists, is proposed to be in a very different region of space, in an orbit that keeps it hundreds of astronomical units from the Sun at perihelion. What Volk's team is suggesting is different. Not a distant solar system member, but an interloper, a rogue planet, or captured object that's in the general vicinity of the solar system, but not strictly part of it, shepherding its own population of smaller bodies. The speculation about Planet 9 or rogue planets or hidden massive objects always makes mainstream astronomers nervous, because it's easy to veer into territory that sounds more like science fiction than science, but the data is pushing in that direction whether we like it or not. We have historical records describing a comet that matches the 3I Atlas behavior 2,000 years ago. We have modern observations of 47 objects with identical chemistry scattered through nearby space. We have trajectory calculations that don't quite fit the simple models. At some point, you have to follow the evidence even when it leads to conclusions that seem unlikely. The Israel Antiquities Authority officially published the 4Q171 fragment findings in January, in a joint paper with Hebrew University and Tel Aviv University researchers. The paper was carefully worded, presenting the text, the translation, the carbon dating results, and noting the correlation with 3 I-Atlas calculated previous perihelion without making definitive claims about causation. The abstract concluded that the fragment may represent an ancient observation of a periodic comet, and that further investigation is warranted to determine if this object corresponds to any known or recently discovered cometary body. Academic caution, appropriate for a preliminary finding. But the astronomy community read between the lines. Within days of publication, there were response papers in preparation, conference sessions being organized, observing proposals being submitted to get more data on the Euclid objects. The Hubble Space Telescope had already observed some of them. Webb was scheduled for more detailed spectroscopy. Now there was renewed urgency, because if these objects really are part of a bound system, if there's something massive at the center holding them together, we need to find it. And we need to understand its trajectory, figure out if it poses any long-term threat to the inner solar system. NASA's Planetary Defense Coordination Office got involved, not because there's an imminent impact risk, but because anything that might affect Earth's orbital environment falls under their purview. They started coordinating with international partners, sharing data, discussing observation strategies. The potential for a massive object moving through the inner solar system, even on a trajectory that doesn't bring it particularly close to Earth, could affect asteroid populations, disturb Kuiper Belt objects, create unpredictable perturbations. It's the kind of thing you want to understand well in advance, not discover at the last minute. And there's the deeper question, the one that people are starting to ask more openly now that the Dead Sea fragment has given the whole situation a historical dimension. If 3I Atlas has been returning every 2,000 years or so, if ancient observers saw and recorded it, what else did they see? Are there other ancient texts that describe similar phenomena, other periodic visitors that we've been interpreting as mythology or symbolism when they might actually be astronomical observations? The search through ancient records started almost immediately after the 4Q171 fragment publication. If one ancient culture recorded 3I Atlas previous passage, others might have as well. And if there are earlier records from previous cycles going back 4,000 or 6,000 years, we might be able to establish a pattern, nail down the orbital period with better precision, maybe even identify other objects from the same system. Dr. Mizrahi's discovery triggered a kind of archaeological gold rush, with researchers diving into dusty archives and obscure manuscripts looking for anything that might reference wandering stars or unusual comets. The Babylonian astronomical diaries were an obvious place to start. The ancient Babylonians kept systematic records of celestial phenomena for centuries, tracking planets, recording eclipses, noting unusual events in the sky. Their cuneiform tablets survive in fragments scattered across museums and private collections, and scholars have been working to translate and catalog them for decades. Dr. Hermann Hunger at the University of Vienna, who spent his career studying these texts, went back through the astronomical diaries looking for entries around the calculated time periods when 3I Atlas would have been visible in previous orbits. If the orbital period is approximately 2,000 years, the comet would have passed through the inner solar system around 2000 BCE, then again around 4000 BCE, possibly earlier, depending on how stable the orbit has been. Babylonian astronomical records don't extend back quite that far in detail, but there are fragments from the Old Babylonian period around 1800 to 1600 BCE that mention unusual celestial events. Hunger found one tablet, damaged and incomplete, that describes what the scribe calls a hairy star, appearing in the northern sky during the reign of King Amisadika, roughly 1646 BCE, based on modern chronology. The description is frustratingly brief, just a few lines noting that the star appeared, grew brighter over time, and was visible for several months before fading. No position details precise enough to verify it's the same object, but the timing is interesting. 1646 BCE is about 350 years off from a simple 2000-year cycle, based on the 5 BCE and 2025 CE passages. That discrepancy could be orbital variation, could be inaccuracy in the ancient chronology, or could mean it's a different object entirely. Without more data, it's impossible to say. Egyptian records from the New Kingdom period offer a bit more. The ancient Egyptians were careful astronomical observers, tracking the heliacal rising of Sirius to maintain their calendar, recording planetary positions, noting eclipses. Dr. Amira Hassan from Cairo University found references in temple inscriptions at Karnak that describe an unusual star appearing during the reign of Thutmose III, around 1450 BCE. The inscription, part of a longer text describing omens and celestial events, mentions a star with a tail like smoke that appeared in the constellation the Egyptians called the Great Bear, which corresponds roughly to Ursa Major and adjacent northern sky regions. Again, the timing doesn't quite match a perfect cycle, but it's in the general ballpark. 1450 BCE falls approximately halfway between the calculated 2000 BCE passage and the Babylonian reference from 1646 BCE. Maybe the orbit isn't as regular as we're assuming. Maybe gravitational perturbations from planets cause the period to vary by centuries from one cycle to the next. Or maybe we're seeing multiple objects from the same system, different comets in different orbits all passing through the inner solar system on overlapping but non-identical timescales. The Mayan astronomical codices were another potential source. The Maya were sophisticated astronomers, tracking Venus cycles with remarkable precision, predicting eclipses, maintaining detailed calendars. Most of their written records were destroyed by Spanish conquistadors, but a few codices survive, including the Dresden Codex with its astronomical tables. Dr. Carlos Mendez from the National Autonomous University of Mexico examined the codex looking for any references that might relate to periodic comets. He found something intriguing in a section that most scholars had interpreted as purely calendrical, a series of glyphs that can be read as describing a celestial event repeating at intervals of roughly 1,872 years in our calendar system. The Maya used multiple interlocking calendar cycles, and this particular interval doesn't correspond to any of the standard astronomical periods like Venus, synodic cycles, or eclipse seasons. Mendez suggests it might represent a long-period comet observation, with the Maya tracking its returns over multiple cycles and incorporating it into their cosmological framework. If that interpretation is correct, and if the Mayan record is describing Three-Eye Atlas or something related, it adds another piece of evidence for periodicity, but it also highlights the uncertainty. An 1,872-year cycle doesn't match the approximately 2,030-year interval between the 5 BCE passage and the 2025 passage. The discrepancy could be Mayan calendar conversion errors, could be real orbital variation, or could be coincidence, the Maya tracking a completely different object that happens to have a vaguely similar period. Chinese records offered more concrete information. Beyond the Han Dynasty reference Dr. Zhang found for 5 BCE, there are earlier mentions in the Bamboo Annals and other historical texts. One entry from the Shang Dynasty period, tentatively dated to around 1059 BCE, describes a guest star with a broomtail, appearing in autumn and visible for a third of a year. That's roughly 4 months, consistent with the visibility duration described in the Dead Sea Fragment and observed for Three-Eye Atlas in 2025. The Shang date is approximately 1,000 years before the Dead Sea observation, which doesn't fit a simple 2,000-year cycle unless the object's period has changed significantly over time. But here's the thing about orbital mechanics in the outer solar system: perturbations from giant planets can alter periods substantially over multiple orbits. An object passing close to Jupiter or Saturn might gain or lose energy, shifting its aphelion distance and changing the orbital period by centuries. If Three-Eye Atlas or its parent system has been interacting gravitationally with the outer planets over multiple passes, the period could have varied from 1,800 years to 2,200 years or more, depending on the specifics of each encounter. So we have a scattered collection of possible historical sightings: the Dead Sea Fragment from 5 BCE with detailed position and timeline information, The Chinese Broom Star record from the same era. Earlier references from Babylon around 1646 BCE, Egypt around 1450 BCE, China around 1059 BCE, possibly a Mayan calendrical reference encoding a approximately 1,872-year cycle. None of it definitively proves these ancient observers were all seeing the same object or objects from the same system, but the pattern is suggestive. Multiple cultures across multiple millennia recording unusual celestial phenomena that might represent periodic returns of cometary visitors. While the archaeologists and historians were digging through ancient texts, the astronomers were doing their own digging through modern data. If there's a massive rogue planet or brown dwarf in the vicinity, something central to a system of smaller objects, modern surveys should have some trace of it, even if they didn't recognize what they were seeing at the time. Dr. Volk's team started reanalyzing data from WISE, the Wide Field Infrared Survey Explorer that mapped the entire sky in infrared from 2010 to 2011. WISE was designed to detect asteroids, brown dwarfs, and other cool objects that emit primarily in infrared wavelengths. Its data has been used to rule out large planets in the outer solar system within certain distance ranges. But ruling out depends on assumptions about how bright the object is, how warm it is, what kind of spectrum it has. If you're looking for a typical rogue planet with expected thermal properties, and you don't find anything, you conclude nothing is there. But if the object has unusual properties, lower temperature than expected, or a different emission spectrum, it might be hiding in the data, misclassified, or overlooked. The team developed new search algorithms looking for slowly moving infrared sources that might have been filtered out as background artifacts or misidentified as distant galaxies. WISE took multiple images of each part of the sky over its mission duration, and by comparing images separated by months, you can detect motion that indicates a nearby object rather than a distant stationary source. Most of this analysis had been done before for the original WISE catalogs, but they were using different search parameters, optimized for finding typical solar system objects or very bright brown dwarfs. After weeks of processing, they found 73 candidate detections. Most were quickly eliminated as known asteroids or artifacts, but 5 remained interesting, 5 very faint infrared sources in the WISE data showing possible motion consistent with an object somewhere between 50 and 200 astronomical units from the Sun. Too faint to be a typical planet at that distance, which means either they're smaller than expected, colder than expected, or farther than the preliminary motion analysis suggested. Follow-up observations are in progress. The Atacama Large Millimeter Array has been tasked with looking at the positions where these 5 candidates appeared in the WISE data, checking for any thermal emission at sub-millimeter wavelengths. ALMA is sensitive enough that it should detect a Neptune mass object even if it's extremely cold, assuming it's within a reasonable distance. The James Webb Space Telescope is also scheduled to observe 3 of the candidates in late February, using its mid-infrared instruments to search for thermal signatures that WISE might have barely glimpsed. No confirmed detections yet. The ALMA observations are still being processed. Webb hasn't completed its observation sequence, but the fact that there are candidates at all, that there are unidentified infrared sources in the WISE data that might be massive objects in the outer solar system adds weight to the hypothesis. We might be on the verge of finding what everyone's been speculating about, the hidden mass that ties everything together. And then there's the Euclid follow-up. Remember the 47 objects with identical spectral signatures? Multiple observatories have been tracking them, measuring proper motions for the ones that only had single epoch detections before. The numbers are coming in, and they're revealing something nobody quite expected. It's not just 6 objects heading toward us, it's more like 15, with trajectories that bring them through the inner solar system at various times over the next 500 years. The earlier analysis only caught the ones with the most obvious inbound vectors. More careful trajectory reconstruction shows a larger fraction of the population is Earth crossing. And they're not all on identical orbits. Some are coming in steep and fast, others on gentler trajectories. Some will pass through the inner system once and leave, others look like they might be in bound orbits that will bring them back repeatedly. It's the pattern you'd expect from a population of objects scattered around a central mass, each with its own orbital parameters but all responding to the same gravitational influence. Dr. Morrison at Harvard Smithsonian has been coordinating the trajectory analysis, compiling data from multiple observatories, and running n-body simulations to figure out what kind of central mass configuration would produce the observed distribution. His preliminary model suggests something between 8 and 12 Earth masses, positioned currently somewhere between 80 and 100 astronomical units from the Sun, possibly in a wide elliptical orbit that brings it closer every few thousand years. When it's at perihelion, whatever that distance is, its gravitational influence stirs up the objects in orbit around it, sending some of them on trajectories toward the inner system.